In this lesson, we're going to take a MapReduce job walkthrough. We'll take a detailed look at the job submittal, at how tasks are assigned and monitored and restarted, which also includes something called speculative execution, which is a failover to handle slow map or reduce tasks. We'll look at how tasks are cleaned up and what happens when the job completes. First of all, let's go back to our players that we had talked about before. We have a client in orange sitting outside the cluster. We have a master node, which in this case is running two daemons, the job tracker and the name node in the same machine. And in our case, we have 6 slave nodes. Let's call them A, B, C, D, E, and F on the bottom. The first thing that happens is the client submits its job into the job tracker. The client has been configured in its mapred site.xml file for the location of the job tracker, and each individual job needs to include at least the map code and one file input in HDFS, as well as the output location of where our output data is written back into HDFS. The client may also optionally send reduce code, and it may also send multiple input paths or multiple directories in HDFS which need to be processed. The job tracker then takes all of these input paths and uses them to interrogate the name node. The name node responds with a list of all the block locations or all the locations in the cluster where every part of every piece of those input files live. From the list of block locations that it gets back from the name node, the job tracker now has a list of places where it would prefer to stand up tasks, or more specifically, map tasks, to process each of those blocks of data. All this while, the job tracker is being pinged by each individual task tracker in the cluster. Each individual task tracker is saying, hey, I'm alive and I have the capability to run this many map or this many reduce tasks. The job tracker is constantly taking these pings and matching them up against its list of preferred locations to stand up map tasks. And it responds to these pings with task assignments. In this case, let's look first at the upper left or the A node. The job tracker, in response to that ping, tells the A node task tracker, hey, you need to stand up a map task to process the first block of this file. And this happens for every block of the file that is being processed. Here we see that nodes B, E, and F also have map tasks stood up. The next thing that happens is that the mappers each read their block of data. Because this block is being read local, there's no network traffic consumed, and it's a very, very quick read. So now each mapper is processing each individual block, and each individual mapper is writing the output for that block to local disk. This data is called intermediate data. Once a percentage of the mappers are finished, the job tracker then signals a task tracker to stand up a reduced task somewhere in the cluster. Unlike the map tasks, the reduced task has no preference for data locality. No matter where we spin it up, it's going to have to copy a significant amount of data across the network. Here we say we just spun it up on node C. The only thing that the reducers can do in the beginning is to copy the mapper outputs. Here we see that the reducer stands up and it reaches out to each of the 4 mappers that ran and copies the output data or the intermediate data into that local reducer. Again, a job may have 0 or more reducers. Here we have a single reducer. We could have used a dozen. We could have used 100. Each of these map and reduce tasks are reporting their progress or their complete or their error back up to the job tracker. Here we see in blue that a single map task is reporting its progress to its task tracker, and that task tracker in those heartbeats or those pings is reporting back up to the job tracker. On the bottom left, we see that our reduce task is doing the same, and it's reporting its progress back up to its task tracker parent process, which is then pinging the job tracker and letting the job tracker know how far it's complete. The job tracker is aggregating the output of all of these pings into a percentage complete, and that's what the client sees march forward in their terminal output. Again, when the client submits the job into the cluster, the job is actually running in the cluster, and the client then just attaches itself to the status file, the output file of the job tracker, so that it sees 0% complete on mappers, 0% complete on reducers, and then 2, 4, 8, 20, 100% complete on reducers, and the same marching forward on the mappers. The job tracker also spins up other map and reduce tasks to deal with any that errored. This also ties into speculative execution, which we'll cover here in a second. Once every one of the mappers is complete, the job tracker sends a signal back out to the task trackers where all the reducers are running. and this tells the task trackers to notify their reducers to run their reduce method. Again, we can only run this reduce method once the very last key out of the very last mapper has been written to intermediate data. The reducers then act as a client. They reach back out to the name node, and they write their output back into HDFS. In the case of a map-only job, each individual mapper would then reach out to the name node and write any of their output back into HDFS. This works the same way that we've covered in other slides of an HDFS file write walkthrough. And then the job is complete, and the intermediate data is deleted from each local disk, and we can see in HDFS the output of the job. Let's zoom in for a second on intermediate data. Again, we said as each mapper works on an individual block of data, it writes its output to its local disk. Again, we call this intermediate data, and it's removed when the job successfully completes. The users can actually end up generating a ton of intermediate data. You're probably going to want to take 25 to 30% of your overall raw disk space and allocate it as a file write area for this intermediate data. Speculative execution is a workaround in Hadoop to deal with any single map or reduce task potentially running slow and making the whole job run slow. It says that by default, if a single map or reduce task is running significantly slower than its peers, Hadoop will try to spin up the same task on a separate slave node. Whichever one of these two tasks that's working on that same input data, be that data a single block in the case of a mapper, or all the outputs of certain mappers for a reducer, we now have two tasks running the exact same function somewhere in the cluster. And whichever one finishes first is going to be used as the winner, and its output will be used for the processing of that block or that set of keys. The other one that was running, which could be the first task or the second task that was spun up, will get killed. This makes sense for the mappers where each input block should be the exact same, but not on the reducers. If you remember, for the mappers, we specify a block size, which says that no individual block of data will be longer than, say, 128 megabytes. And every single block will be that size or smaller. So each individual mapper should probably run about the same speed as every other mapper in the cluster. However, reducers may not use that exact parallelization function. Remember that we have two reasons that we run multiple reducers. One is to simply parallelize the reduce function, so that if we have 100 reducers running, the overall reduce function will run 100 times faster than if it was running in a single reducer, or to leverage the fact that MapReduce writes one output file per reducer back in HDFS. We can use this to bucket by organizational or temporal dependencies. For example, if I was Amazon.com and I wanted to run a MapReduce job to analyze my sales based on the month, I could route my keys such that all of the January sales numbers go to one reducer, all of the February sales numbers go to a second reducer, and so on and so forth. Again, if we did it this way, our January and February reducers are probably not going to work that hard, whereas our November and December reducers may work significantly harder because they're processing data from the Christmas shopping season. Again, we parallelize the function somewhat, but in this case, the reducers for January and December are going to run probably at least 20% slower, if not 200 or 500% slower than the January and February reducers. It's our strong recommendation to turn off speculative execution for the reducers. It's on for both mappers and reducers by default. You can control this by setting the MapRed reduce tasks speculative execution variable to false on the job tracker. When a job is complete or finished as being dictated by the last mapper in a map-only job or the last reducer in a map-reduce job, when that last map or reduce task is finished, that map or reduce task will signal its task tracker, which then signals the overall job tracker that the job is finished. What happens is an _success flag is dropped into the specified HDFS output directory, and the job tracker reaches out to all task trackers and signals them to remove their intermediate data that was written by each of the mappers. Log files, however, still persist. The job tracker contains logs for the overall job, which it keeps in the job tracker's local disk, as well as the specified output directory in HDFS. Right next to that _success flag, we also have an _logs directory, which has the overall output for the logs. The task trackers on each machine where a map or reduce tasks also persist logs across every map and reduce task which was run. And that's it for the map and reduce job walkthrough. We covered a detailed look at the job submittal process, task assignment and monitoring, speculative execution, task cleanup, and job completion.